So we are talking about capacitors, and you've probably watched the videos on capacitors, hopefully. And so a capacitor is two metal plates Now, in general, we're going to talk about just having air between the two metal plates, but if you look, there's going to be some material that they put between the plates, which is going to be a dielectric, which is going to make the capacitor stronger. So, dielectrics Okay, so dielectrics between the plates make the capacitor stronger, but we're ignoring that effect. Okay, so we're going to assume that we have plate, air, plate, and then we have like little wires coming off. Now, we have this thing, capacitance is how big the capacitor is. So is C, and it's measured in farads, which is F. Okay, so now there's two ways that we can come up with how big a capacitor is. So there's two things. Is we can actually talk about the physical dimensions of the capacitor. So I gotta remember, epsilon naught is not one of those numbers that I have off the top of my head. So we have capacitance, which is C, and now we've got epsilon naught, which is the permittivity which is a really, you don't really need to know that. What you need to know is it's a constant. And it has a value of 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. Okay, so epsilon naught is just, and I'm going to call this epsilon naught. That's how I'm going to call it. And then we have A is the area of one plate, because we're going to assume that both plates are the same size, and that's going to be a meter squared. And then D is going to be the distance measured in meters. Okay, so we actually just sort of have this idea that by measuring how big the capacitor is, we are actually literally measuring how big the capacitor is. So if we make the area of the capacitor, if we make the plates bigger, the capacitor is going to get bigger. If we put those plates closer and closer together, the capacitance is going to increase. So the way that we make for a big capacitor is we have the largest area possible separated by the smallest, and the plates are separated by the smallest distance possible. So there's one equation right there for the size of a capacitor. Now another way to measure the size of a capacitor is we have C equals Q over V, where Q is the charge on the capacitor, measured in coulombs, and V is the voltage on the capacitor, measured in volts. So So two ways to think about it is a big capacitor. I'm going to throw this equation up here just so it's up on this page. A big capacitor is two big plates separated by a small gap, and a big capacitor holds a lot of charge at a low voltage. Okay, and as you saw, like basically in the videos that we watched, the goal is to get the biggest capacitors that you possibly can, so you can do stupid stuff with them. Okay, and so then the last equation that I'm just going to throw out there is PE equals 1/2 QV, and that's the potential energy on a capacitor. Okay, and so I think that's where I'm going to leave that, and then we're going to do some capacitor equations here in just a second.